Good morning from the American Academy of Ophthalmology Conference in Chicago. We're pleased to be here today with Dr. Michael Snyder from Cincinnati, Ohio. Thanks a lot for being with us this morning.
It's really a pleasure to be here.
I'd like to speak with you this morning about a really important new IOL formula called the Hill-RBF 2.0 formula. This is an artificial intelligence-based IOL formula that has really helped a lot in terms of improving accuracy of IOL calculations. Can you explain for us a bit how it works and why it has helped to improve accuracy in calculations?
Well, the RBF formula is really amazing because it's using an artificial intelligence-based program, and it doesn't really care about the divergence formulas. It doesn't really care about the optics of it. It's just basically looking for patterns, and it can detect subtle patterns within large data sets, and it doesn't matter what features are the most important to us. What it does is it detects what's going to get the result that we want, and so it can predict very, very well. The thing that's most exciting about the RBF and the intelligence-based nature of it is that it is a constantly improving system. With the original RBF, we had the best data that we've had from any other mechanism of calculating IOL powers, and each time we add new data to the system, as it has now happened with RBF2, it just gets better and better and better. And so the formulas that we've used in the past that are based on vergence and based on assumptions about the shapes of the eye are really not important to how the RBF works. What's really exciting for me is that each time we use it, we collect more data, we get better and better, and the 2.0 is now even better than the 1.0 system in the high axial myopes and the high axial hyperopes. The hyperopes have been the toughest ones to catch, and the original RBF, we did a prospective study on that, and it basically blew away every other mechanism of calculation on a head-to-head comparison, and the 2.0 is now getting into the non-ophthalmic eyes as well, and the wonderful thing about it is that it will also tell us when it does not have enough data to select. If it doesn't have enough data in that database for a particularly unusually shaped eye, it'll say, I don't have enough data to make an assessment, and so that we won't inaccurately choose something wrong. Whereas a vergence formula, every once in a while, it will just make a mathematical computation when it doesn't have any data upon which to base it.
Well, that brings up a really good point, because I think, as you mentioned, in some of the other formulas, if there's missing data, the formula may just go ahead and produce a result anyway. Here, in this scenario, if the data is not complete, if the formula does not feel that it has enough accuracy to predict the IOL power, it will tell you so. But what do you as the clinician do in that scenario? You're faced with a situation where the formula tells you, look, I don't have enough information for accurate prediction, but I can give you a range or a ballpark. Do you still go with that value?
Well, you do the best that you can. If we're looking at a vergence formula, for example, I had a patient a little while back where I plugged in the normal data to a vergence formula, and it was an extraordinarily long eye. I think it was about a 33 millimeter eye. And the vergence formula for our calculations just gave me a number which didn't seem quite right. And in fact, it seemed quite a bit off. So I used the same system and started fudging it a little bit. I said, well, what if I make the K's a little flatter? What if I make the length a little bit longer? And we found that there was this spot where the mathematical computations just really made the formula highly inaccurate. And so that would be a setting where I would just have to reject that altogether. The RBF, if it tells you that it's right, it's got a 90% confidence interval of being within the boundaries, then that's going to get you a great result. And if the RBF formula tells you that it doesn't have enough data, well, then you have to look at the kind of eye, look at whatever the next best formula that we may have available for that kind of eye might be, and do our best guess. But in those instances, it is a best guess. What's useful from my perspective is that gives me the opportunity to tell my patient that we have limited data and that there might be a greater likelihood that we might not hit as close to target, and so there's an expectation set up front.
Well, Michael, this has been a really great discussion for us about how the Hill-RBF 2.0 formula works and why it's helpful for us, especially in the extremes of axial length. Thank you so much for being with us and sharing your expertise.